3, 2, 1, go. And we're live. This is Retrace segment number 97 for Tuesday, December 27th, 2022, 10 p.m. Eastern, 7 p.m. Pacific. Retrace is about what's going on out there. The short answer to that is computer control. We are toward the end of the December to Remember Math and Code event in preparation for our deep dive study of AIMA4e, Artificial Intelligence, A Modern Approach, Russell and Norvig, 4th edition. You didn't know this? There are all these videos about it. You haven't watched any of them? You're starting at part 15? Don't start at part 15. Actually, do start at part 15. That's the whole purpose of part 15. This is 15, isn't it? Okay. We gotta summarize. We gotta make it so that you don't have to watch all the first 14 if you don't want to. We're gonna get into the length method and the straight line distances. Okay. So let's do it, shall we? Jump over to the code. This is the same source file that we used for Re97, although I did make changes and improvements after yesterday's live stream, as we will probably discuss. This has got a lot of stuff in it. If we comb through this whole thing, there's just, how many lines is it? It is 304 lines, and some of that is, just like colorization, not important. Some of this stuff, I don't think we're using all of these imports. Not for this particular program. So anyway, wait. All right, let's slow down a second. We're doing a recap. I can't start with the source code. Holy crap. What am I thinking? Let's start with the pictures that give us the context. Okay. This is the AIMA4e homepage. Okay, that doesn't help much. That's not a picture. Okay, here we go. This is seriously? No, I'm not searching for next word. I'm doing that for something else. I'm searching for Romania. Show me Romania. There we go. This comes from the book. This is the figures document that's available via AIMA's official website, as you can see in the URL bar there. And this is a map or a representation of a road map of Romania. These are the cities in Romania, and we need to get, for our toy problem, our best first search on page 73 of AIMA4e, get from A to B, from Arad to Bucharesti. Which I am definitely sure I'm pronouncing correctly. In order to get from A to B, we are going to have to find our thing again here. Everything went pear-shaped. There we go. We're going to have to, so we call this our state space. State space. This essentially shows actions. It's not a formalized state space, but it's a representation of a state space. We're going to have to superimpose a search tree on our state space, which is what this maroon thing looks like, crawling across the map based on some rules that we give it in a program. The source code that we're working from, that we mostly copied into our source program, comes from AIMA4e's official GitHub AIMA-Python repository. Okay, so look for that. Links will be in the show notes, of course. And then we started this whole journey at Re82. What is a problem? Really, the whole point of what we were setting out to do in this, remember, this is the December to Remember Math and Code event. The purpose of this is to front load, our December work is to front load the hard parts of studying AIMA4e so that January to June 2023, we're not going to get stuck on spend 2 weeks on a Python implementation because we're not good programmers. And by we, I mean you. No, actually, I mean me. So when I started this particular project, and really everything that I've done this December to Remember that actually started in late November, I didn't know how to do the things I was doing. And it's especially apparent with the Python work that we had to do to get Best First Search up and running. But it is up and running now. So crucial to remember here as we work through this quick summary is that we're not trying to learn the AI. It's inseparable. Like, it's impossible to make sense of the code if you don't learn some of the AI, but we're not trying to master the AI concepts in this. We're really just trying to get the program to run. Really, no more than how do you pass, and this is the pseudocode, okay? This is pseudocode. If you're not familiar with that, you're going to have to take a few steps back. How do we pass a problem and an evaluation function to a program? How do we get this pseudocode that looks like this into something like this that actually works? And by the way, you can go to their IPython notebook, that's what this is, and you can try and run this stuff, and it's not going to run for you like ours is. Even if you can get it to run, you really have to know the guts of it to make it do what you want, or to really be sure that you're doing it right. But the way we built it, you don't have to you don't have to wonder because it's chatty. I'm going to quickly mention as well, out of between Re82 and Re95, which is the last one before today. So Re82 to Re95 are the best first search. I don't think there were any. Yeah, that's all we did, right? I don't think any of those are not related to best first search. We had Re82 set the stage, talked about formalizing a search problem. This is important stuff, state space, initial state. What is a problem? I mean, again, this is all squishy English words. Okay, does not tell us what the code is, or it's not the code, but it gives us a hint, and if we know what we're doing, we can get from here to the code, and now we sort of do know what we're doing a little bit. But this is how we have to start thinking about problem in pseudocode. We have to start thinking about it with this formal structure. On Re84, we talked about the formal structure of a node. Nodes are crucial. So when you're building and superimposing this search tree on the state space, what you're doing is reaching and expanding nodes. And as you reach a node, you add it to your reached frontier, and as you and then once it leaves the frontier, it becomes part of the. It can be part of the frontier and reached, but once it's no longer part of the frontier, it's just part of your reached nodes. Anyway, a node is not a state. A state is like a city. We represent them with single letters in the source code. But a node can correspond. No, a node corresponds to a state, but more than one node can correspond to a state because a node has a bunch of other data that goes with it. What was its parent node? What was the action applied to the parent? What was the path cost, the cumulative path cost at the parent and now at the current node? And the reason you need all that data is you need to be able to find your way back. Once you have a solution node, you need to know like how you got there. The solution just can't be, hey, I have a node that corresponds to the state you want to be in. It has to have a bunch of other data in order to be a solution to the A to B problem, and it has to be not recursively enumerable, but I want to say that phrase for some reason. You need to be able to take your solution node and find out all that other information. All the information that's not directly part of that node, you need to find out about its parent and then its grandparent and then its great-grandparent, etc., which we will do today. We didn't demonstrate that yesterday, but that's in the source code for Re95 now. Okay, so nodes and states need to be carefully distinguished. So have a look at the structure of a node in Re84. In Re90, we take the formalization of the idea of a problem further by adding notes on the implementation of each one of these components of the problem. This is as of Re90. I'm sure there's some updates I could do to it since then, but this is good enough. I was happy with this at Re90. This tells you. It takes you from the squishy English to an explanation that and references to the code in the implementation that corresponds to that squishy English. Okay, so Re90 is good for that. Re95 is the one we just did yesterday, and this is the ultimate execution. This is the ultimate form of the program. It's very chatty, but we're learning, so it needs to be chatty. It walks you through every step. By the way, if you're wondering, the reason that the len method was called is because it's part of the while loop. Okay, so it's the while test, and the while loop is what's calling that priority queue len method on Frontier. That's why that happened. We were confused about that. And then the other thing we were confused about yesterday was why these heuristic numbers didn't correspond to. So like let's say. So we're here, the straight line distance from, I guess it's the last node that we're at, F. The straight line distance from F to B, let's see, from F to B, where is it? Oh, geez, 176. Okay, so here, the straight line distance, I'm not going to be able to give you an example quickly here. But the idea was that like from A to S, can I show that? No. Uh-oh. What happened to my thing? I lost. Oh, crikey. Did I crash it? Come on. There we go. A to S. I just need to find this in the output there. No. Dagnabbit. That doesn't normally happen, but which is a good Alt-Tab program, but it's not perfect. What am I doing? Here we go. Okay, so from A to S, the path cost, so the straight line distance, the heuristic, let's say from A to Z, is 374. there, and we did the math on it. Oh, there's always something that gets me. And okay, we're just going to go to the GitHub, our GitHub. Bang. Okay. Where was it? We did the calc on this. Here's the calcs. I didn't print this in any of the notes, but I probably should have. From A to S, we have these are the two coordinates of A to S, and then we're saying it's 116 from A to S. And if you run that for our toy problem, our T problem, then it lined up, or I thought it did. But from A to S here we have 140. A to S here says 140, but A to S in our calculations as shown right. Okay, we're at A node. We expand its child nodes. We get Z, S, and T. S is the shortest, 253 out of these numbers, okay? Why is it 253, 374, and why is S closer than Z and T? Okay, S, Z, and T. The reason is that these, I can't prove this to you, but this definitely makes sense. These lines in our state space graph do not represent straight line distances. They represent road distances. Okay, so they're a simplification of a road map. What is a road map? Look, I thought I could show one. Can I show it? No, I can't really. I had one. No, never mind. Okay, so you can sort of see that. Like if you look at this, 75 plus 71 is going to be more than 140. Fold this over. It's almost, to me, it's very clear that this 75 to 71 is shorter than this 140, which is not possible if these straight lines are supposed to represent straight line distances. And of course they don't. A simplified road map of Romania with road distances in miles. So it's sort of confusing that we see straight lines between states here, but these are not the straight line distances. These are the road distances. Imagine them winding, over the river and through the woods to grandmother's house we go. Whereas if we are calculating for a heuristic the straight line distances, first of all, we need coordinates, which our nice state space graph does not have. We do not have coordinates here, but they're provided in the AIMA implementation here. Okay, these are our coordinates. Why does that keep happening? That's going to drive me nuts. Actually, no, it's not so bad. Okay, we need coordinates, and we don't have coordinates here. And anyway, enough. Have I convinced you? This is our implementation with the chatty implementation is properly sorting in our priority queue, putting the top node with the lowest evaluation function value, 253 versus 374 versus 329. Okay, and it sorts 253, 374 first before it adds 329. So it's not always sorted, but the top is the one that matters. The top always, you can add whatever you want to the priority queue as long as it's greater. It'll but if it's got a lower evaluation function value, then it's going to be at the top. Otherwise, it doesn't matter. Okay, so should we keep going with that? So yeah, we're going to show this in action, but this is the printout of the code. The other thing that I answered why the straight line distances don't match the graph, because the graph is of road distances. The other thing I did was I added a while loop to print the parents in reverse order. I wanted to print them in normal order, from A, S, F to B, and I wanted these path costs. These correspond to the road distances, not the evaluation function, which is straight line distances. I wanted to print them individually so we could sum them to 450, but you can check this, run this code on any problem and you can check the path costs and you'll find that they're correct. Because before we had this little while loop, all we had was the node, its path cost, and we didn't really have any way of inspecting. Certainly, we didn't even have the path drawn out unless we looked at this chatty output. So I added that to the end of the program. And I added some notes explaining the other things that I did there. Okay, so let's go watch the program run. Okay, in the demonstration in the notes and for our purposes in this project, we wanted to get from A to B. So that's route problem R1, the instantiation of route problem R1, and we're going to use our evaluation function F1. Okay, so it's just going to be R1, F1 as we did yesterday, but this time we're going to see just basically what you saw printed to screen there. Okay, so we go to IPython and we load our file, and then we do best first search R1, F1 is in my memory. You'll probably have to, if you run this, you'll have to type R1, F1 the first time you do it, but then, okay, now let's look at it. Okay, this. So you're just seeing the same output that is printed in the notes from Re95, and we can follow along all we want, and everybody will be happy. I find it useful to look, to keep track of this, like short of actually graphing this to a visualization, keep track of the nodes, the node values, because when we're in this while loop, in these, it's more than one, just while loop, hang on, bang. So let's go best first search. When we're in the while loop, and then there's also a conditional and a for loop. So this part of the code checks whether or not you've found the goal state, and then returns the node if you have. And also now with the while loop or the while not loop that I put in there, it also returns the parent information, which is crucial. And then if you don't have the goal state, then you go back and expand the children. Oh, so we're talking about expansion of nodes here. That's this thing here, okay? And then you analyze each child to see if it's more or less valuable than the children you've already found, and you add them to the frontier and the reached. You add them to reached here, and you add them to here, frontier here. And then once you get done with that, then you go back to the top of the while loop. And this is where the len method is called from priority queue, because you have to check whether frontier, while you have to check whether frontier is still has a length, I guess is the way that we should say that. And if it doesn't, then you return the failure node. That's what's down here. Failure is actually a node. It's defined up here. But anyway, we don't have that problem. We could give it that problem. Oh, come on. No, I didn't want that. That's fine. Okay. Okay. So this is where all the action happens, obviously, in best first search. But best first search has all these dependencies that we've been looking at. So starting at the top, importing some tools, nothing really crucial, but definitely the default dict and the DQ. And I don't think we used counter. I don't think we used any of the other stuff. Did we use any? Oh, heap queue. We used heap queue as well. This import list is from their source code from the AIMA-Python source that I just, I copied only what I thought I had to copy, with the exception of this import pile here. I had to copy class problem. I had to copy node. I had to copy failure and cutoff. I had to copy expand node, path actions. Did I have to? I don't remember if I had to do that one. Path action. No, I didn't. No, it's not in there. Okay, but I know, this file is search4e. It's for more than just best first search. So you got stuff put in there, and maybe the reason I had to create that while loop for the parents. Maybe these two things would have, but they're not part of the best first search that they implement. So I didn't go get them. But anyway, we'll do more of this later. FIFO queue, LIFO queue. I don't think anyway, I don't know. Obviously we did a lot of work on priority queue, made it very chatty so we could follow it. And then here's best first search. Okay, this is the first one. We just sort of built on this, made it very chatty, added the while loop to report all the parents or the ancestors of our, and then we've done nothing below this line. Actually, I did grab some just some hints about how to implement the evaluation function, because there's no evaluation function implemented to this point. So, and this is best first tree search, where they first do they do an F in here? I don't even see it in here. They start to do them down here, A star and A star tree. They have F, defined by a lambda here, but they don't do it until here. And if basically, if we hadn't implemented some sort of, first I did a dummy evaluation function, because if we're not doing, if we remove it, then we're not satisfying our goal. We're not figuring out how to, where is it? We're not figuring out how to pass an F. You know, we figure out how to pass a problem, but not an F. Well, we got to figure out both. Those are the two things that we cared about here. But if we make the evaluation function something dummy, just like return this value or return always return 1 or always return 0, we can't really see if we're doing it right. We can't really see that sorting of the priority queue based on that F. That F is what sorts the priority queue, and you can see it in the pseudocode. Frontier is sorted by F, okay, or ordered by F. Where is that happening? That is happening in priority queue. Here, no, do it. Actually, you know what? Window swap states. Can we do window swap states? There you go. I like that one. I think I have that key binding, but I don't remember. Search class prior. Okay. So that sorting is happening here, really, because the initialization of priority queue doesn't actually have to sort anything, because it's only taking one node as it needs the key, which is what we call or what priority queue calls our evaluation function. That's the key right there. But the sorting happens here when you're adding a node or an item, based on a node, to the priority queue. Then you have to use the self.key. The method use the key as a it's an attribute, but it's a callable function, so you can pass it item, and so then you've got your score. So when you see in this list either yellow or pink, when you see like a number and then a thing between Pacman brackets, greater than, less than, what you're seeing there is the score and the node. Okay, that's this here. Self.key of item is the score, and then item is the node. Okay, and then once you've remember, we're here doing the add method in a priority queue, and our priority queue is the frontier. Frontier is this. Okay, so frontier is an instantiation of priority queue. When we add an item to heap queue, we need to have, it needs to have a score, and then heap queue is the pop what's going to, I don't know, I'm not sure exactly which part of this puts the lowest number on the so for me it's not the initialization. Key.item this heap. Okay, you just heap push, heap queue. Oh, is heap queue? Okay, let's just, I've looked at this, Python heap queue, and it's okay, yeah, this is like it's a binary tree. Every parent node has a value less than or equal to any of its children. Okay, so that's this implementation that's called heap queue is what's doing our ordering, really. Like at the lowest level, it's using our evaluation function, but the evaluation function is not doing the sorting. It's this heap queue tool. Anyway, I've got to stop somewhere, so I don't really understand the guts of heap queue and heap and its methods. Okay, so that's what you're seeing when you're seeing priority queue. Self.items, as we see here, is always the same as frontier.items. They're the same. It's the same data in memory. I'm just printing. I have a print in the instantiation in the class itself, and then I've also added print statements in the best first search function. So that's the difference between what you're seeing there. But it's crucial to understand priority queue as being frontier.items. Like, the class ceases to be relevant after the instantiation of it in frontier. But we can sort of compare the two and make sure that we understand the connection by printing both of their items. Okay, here's the reached dictionary. These are just the states and the nodes that we've reached already. The frontier is priority queue and frontier, and so those are the nodes that we haven't expanded yet. And then every time you get to a while loop, you start reading children using actions in the actions dictionary. Well, let's just go all the way down. These are it's called links, but it's really the actions. So let's say we reach a node that corresponds to state O. Okay, O has action O to Z, cost of a road distance cost of 71. It also has action of O to S, road distance cost of 151. And then A is the easiest one because we've done so much work on it. A goes to Z, S, and T with these three costs, road costs associated with it. Okay, so when you see the expansion and evaluation of these child nodes, so like let's just walk through, like we're at S here. Okay, so the node that we're at is S, and here's the frontier. And actually, can we? Yeah. We stayed. So we popped off the frontier. We were at node A, and we popped off the. We did our work here the work done at node A is this. Okay, and we basically used the evaluation function to check the heuristic, these straight line distances, to find the lowest one, and then and at each one we added it to the frontier dot items, and then that heap queue has at the top, it always has the lowest straight line distance, and once we're done with all the children, then we have to change nodes. We have to go from A to S. S here at the last. Just before the pop, okay, that's the lowest scoring item. So we pop it, and now we're at S. Now we got to start the whole thing over again, and jump into the child for loop, okay, and we evaluate all of S's children. S's children are A, so you can see they're easiest to. And by the way, the states that are in this column here, like this, above and below these columns, they're the nodes that we're at, and that's our value of node. These underlined letters that are not. I wish I could have gotten them to print as nodes, but they're printing as states. But anyway, it doesn't matter. It's not that important. These are the children being analyzed. Okay, so S children. Let's check it. Can S go to O, A, R, and F and no others? Okay, let's check our thing. What did I say? O, A, R, and F. Okay, we're at S. We can go to O, A, R, and F. Okay, that's inspires confidence, right? These are the children of S. You can go backwards. The A is not really a child of S, but it could be. An action applied to S that takes it back to A makes a child and a parent of S. I don't see any issue with that as long as we're not in directed situations. That's fine. Okay, so now we're at S for one last moment here, and then we switch to F. Why? Because F is the lowest heuristic score. Lowest straight line distance. It's just a heuristic. It doesn't actually produce the best path every time, but it produces a path that's guided by some information. So we just repeat that until we get to the part of the code, def best, the part of the code where we're done down here expanding the children. It's expanding and analyzing the children for our current node. We go back up to the while loop, and we change the frontier, we change the node to whatever value of those children was the lowest, and then we check that node to see if it's the state, and if it's the state, we get an output. The output. Oh, geez, crikey. We get this. Okay, we get data. We get what we wanted in the first place. Information about the node itself. It's what's it called and what's its cumulative path cost. Here I'm printing the parents, what do you call them? ancestors, and then the state that it corresponds to, which is our B. B is our goal state, and then the number of hops, and then the parent is F, and actually all this stuff. I don't really need this latter stuff because this covers most of it. But anyway, let's prove to ourselves that we are actually doing what we think we're doing, and run a couple more problems. Let's do best first search on R0 and F0. Very easy to go from A to A. That's what R0 and F0 are. If you don't remember, these are the various problems that we can run. Let's do R2 using F2. We have to match these. We don't have to, but these numbers are the way I've written it. They're meant to be matched. They don't have to be, but then you get kind of weird results. Oh, look at that. That's a long journey. So we started at. Okay, what are we doing here? We're going from, what is it, 2? From N to L. N, I, V, U, B, F, S, R, C, D, M. I have a feeling that straight line distance is not a good heuristic for that particular journey. What? N to L. Let's have a look. N, where's N? Ooh, oh, well, you got to do a lot. Look, you got to hop 3 nodes just to get out of the N neighborhood. N to L, where's L? Oh, yeah. No, this straight line might have been really good. Look at how many places you got. Look, these places are just not near each other. They need an airport, like we were trying to build with gradient descent. But anyway, we didn't get around to that, did we? We did the gradient descent, but we didn't build the airport. Let's do one more and then call it done, shall we? 3 using heuristic or evaluation function. 3. Okay, not so long. We're going from E. Whoops. We're going from E to T. Let's just check that to be sure. E to T looks good. Let's look at the map. E, where's E? I don't know where E is. I find it hard to find these letters. E is here. T, wait for it. T is way over here. Oh, is that the T? Oof. Okay. Is there another T? Are we really? All right, we're going to have to check this one. E goes to HUB. 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 So far, so good. From B, it goes FSA. B goes FSA. Look at that. This thing is smart. I looked at this map. You're building these machines to do things so you don't have to use your brain. Good thing, because my brain's not so good. I looked at this map, and I did not see that path. I did not see that excellent path. I was thinking we're going to have to go through here, and that's what made me doubt it. No. AI smart. Retraice guy, dumb. Okay? So it went to FSA and then T, right? That's what we saw? Is that what we saw? FS, so just so you know where I'm at. FSA and T. And the path cost is 837. Sounds about right. Nothing crazy there. Okay. That's what the code looks like. That's the fun and games. If you want to go a little bit deeper into what we did, but you don't want to commit to the 15 episodes, there's one more thing you can do. I will pull it up here so that you can see. Where is it? I didn't even. Oh, it's in. It's okay. Give me a second here. You're going to have to bear with me while I pull up what's going to be published early tomorrow morning. Here, open. Let's see. Notes, PDF. Yes? We're in Re97, right? There we go. Okay, so this is the abstracts from all those segments just in one place. This will be published. This is not online yet. This is today's segment. So there's an abstract for this segment, and then one for each one of the segments that we did to get here. And and it's also a good way of, like, if you're not sure, where do we do this, where do we do that, you probably check, keywords, just doing Command and Control F. Where do we deal with, what was it, the multi-map? Okay, so there's that's the first one. In this context, there we go, we're highlighting it. It only does one page at a time, I guess. But anyway, we did several parts on multi-map, and that's how you find it and that sort of thing. Okay, that should be useful to you. Enough. We're still in the December to Remember Math and Code event for 4 more days, 4 more awesome days. I got to show you, in the next 4 days, we're going to cover all of these books. No, I'm just kidding. But we have to be ready for this stuff. And and I'm going to try to be in 4 days. But we're not going to be ready, and we're just going to go head first because that's how real life is. So December to Remember continues. This has been the Best First Search project, and now in about 25 minutes, we're going to talk about ChatGPT a little bit more. There's more to say about it. I thought I was done yesterday, but no. We're going to do a 3-parter on that one. All references and notes and everything else, all the good stuff is at our website, retraice.com, retraice.com. GitHub, AIMA stuff. AIMA.retraice.com is useful. Notes.retraice.com is useful. Do we have a links.retraice.com is useful. Okay, anyway, enough. Signing off for now. We'll see you in 25 minutes.